Today we'll be talking about hidden Markov models. This is the last core topic of this class. After we talk about hidden Markov models, everything else will just be some advanced topics, maybe that talks more about research, and then review in case people have questions about anything in the class. So the next two lectures are on hidden Markov models, and that's the last core topic we'll be covering in this class. So we're going to talk about sequence predictions. We talked about sequence prediction just a little bit when we talked about embeddings, although I sort of glossed over most of its complexity. We just talked about sequence prediction in the context of basically some sort of logistic regression problem. And today we'll be talking about sequence prediction a lot more in depth. And we'll do so from the perspective of probabilistic model. Okay, so let's start with perhaps the simplest form of sequence prediction that is studied in machine learning, and that's in the context of part-of-speech tagging in natural language processing. So X is a sequence of words. In this case, you have three examples: a fish asleep, the dog ate my homework, and the fox jumped over the fence. And the goal, or one of the goals, is to be able to predict a part-of-speech tag sequence on this input sequence of words. So, for example, in the first one, we would predict noun-verb. In the second example, we would predict determiner noun, verb, determiner noun. And the third one, we would predict determiner noun, verb, preposition, determiner noun. And so there's some vocabulary of the words and some vocabulary of the part-of-speech tags, and the goal is to model this pair of sequences. So again, we're going to approach this from the probabilistic modeling standpoint, rather from a like an embedding learning standpoint. Of course, next week in our more advanced topics classes, you'll learn about some connections between the two. Today, we're going to look at it from a purely probabilistic modeling standpoint. So what are some challenges in sequence modeling? Well, it's a multivariable output. We want to make predictions over multiple things simultaneously, for example, over multiple tokens in a sequence. And furthermore, it's not just multivariable. The number of variables is itself variable. So in other words, it's a variable length input-output. Because sentences lengths are not fixed a priori. They can vary in a real corpus. And so one way to think of multivariable outputs, and again, I'm going to start really, really simple and just build up from a very simple ideas. So let's take this example, fish asleep. And then in this case, the associated part-of-speech tags is the sequence noun-verb. Let's suppose for the sake of argument that there are 6 possible part-of-speech tags, although in practice, of course, there are many more, but there are 6 sort of high-level ones. Determiner, noun, verb, adjective, adverb, and preposition. There are others as well, but let's keep it at that level. And one way is to say, well, why don't we just treat it like a multi-class prediction problem, which is something that we sort of touched on in this class, where we keep a weight vector per class, and then we score for an input we score the class score for each class. And then we predict the class with the highest score. So this is a standard multi-class prediction paradigm. One question is, okay, well, how many classes are there if we're going to model it this way? And by the way, this is exactly how, in the deep learning lecture, when we're training the ImageNet classifiers and convolutional neural nets, there's just 1,000 classes, and the top layer of the neural net has 1,000 heads that looks like this. Or 1,000 sets of weights. But let's say for this problem, how many classes are there? Well, for this type of problem, we want to predict all possible, at least from this perspective, we would want to predict all possible length m sequences as a different class, where m is the length of the sequence. And so, just as an example, we would have to run a for loop over the score of determiner, determiner noun, determiner verb, and so on and so forth for this input fish sleep. And after we computed the score of all these different combinations, we would pick the class that has the highest score. And so the problem here is that the number of classes is L to the M, where L is the size of the output vocabulary, in this case 6, and M is the length of the sequence that we're predicting, in this case 2, but in practice pretty much bigger, but even for 2, length 2, there is 36 classes. And this number grows exponentially with the length of the sequence. So this is no good. And so this is not good from both a computational and a statistical point of view. From a computational point of view, we'd have to write a for loop over an exponential number of things. That's no good. From a statistical point of view, we'd have to estimate parameters of an exponential number of parameters, which is also no good, because the data requirements there might be huge. Okay. And so, this is one of the perspectives that sort of started to motivate things like hidden Markov models, because a very naive and what people in probabilistic modeling would call unstructured, an unstructured approach to this problem would lead to basically unstructured means every combination is treated as a unique class that has no real relationship to any other class. That's what unstructured means, and this requires an exponentially large parameterization of the model. Okay, so let's go to the other extreme, just to sort of go through this thought exercise. And now I'm going to predict the part of speech tag of every token in this input sequence X completely independently. So now this is an independent multi-class prediction per word. So for example, I predict the part of speech tag for I independently. I predict the part of speech tag for fish independently. I predict the part of speech tag for often independently. And then I concatenate the predictions. So this is the other extreme. And now the number of classes in any specific multi-class prediction problem is 6, in terms of, because those are the 6 part of speech tags. So now we can, this is something that looks like something that we can, shoehorn into one of our existing supervised learning frameworks, and we can just run it and solve it, and it should at least run and finish. And so you get something that looks like this, where if the prediction model is otherwise unstructured, then we would just learn this probability table of probability distributions of y given an individual word. Again, this is a really simple example, but this failure case is generally holds. So, the correct prediction for I fish often is noun, verb, adverb. But our approach in this particular simple example predicted noun, noun, adverb. In particular, fish was predicted as a noun, whereas in this particular sentence, it should be a verb. And so our model made a mistake. And this would be a kind of mistake that might happen very often, because context matters. Independent predictions ignore context. It is a very extreme example. It ignores any context except for the word at this location in the input sequence. But in general, even if you condition on a bounded window of context, you still can often get this problem where in isolation, at least in this very, very simple example, in our training set, let's say, fish is more likely to be a noun. But in the context of following a noun or a pronoun, and I guess I'm lumping pronouns and nouns into a single category noun here, just for the sake of simplicity, fish is more likely to be a verb. And these types of conditionals are very can be very complicated, or it can be hard to define. And so this is just one toy example that illustrates that context matters. In particular, this particular kind of context is called a first-order dependence. And a first-order dependence is captured by modeling all pairs of neighboring elements in a sequence, in this case, all pairs of words. A second-order dependence, which is something we're not going to be talking about in this class, but you should just be aware of, considers all triplets. In an arbitrary order, dependence gets you back to the exponential size problem, where you get this exponential blow-up. Any questions about that? Okay. So that leads us to the first order hidden Markov model, which would be the topic of this lecture and next lecture. And there's a few different ways to define the hidden Markov model. I'm just going to give you one definition that's fairly common. The goal is to learn a joint probability distribution over XY pairs, where X and Y are both sequences. X is typically, at least grounded in our example, X is a sequence of words, and Y is a sequence of part of speech tags. And so a first order hidden Markov model is fully described by the following probability tables. And again, we're just like in naive Bayes, we're going to factorize the joint probability of P of X comma Y into a bunch of products over smaller probability tables. And I'll show you how they all add up in the next slide. But these are all the probability tables that fully define a first order hidden Markov model. The first one is P of Xi given Yi, which is the probability table of observing observing the word Xi, so the word X in the ith location, conditioned on the state Y being in the ith location. So conditioned on this particular, conditioned on the ith token in the sequence being this particular part of speech tag, what is the probability that we would observe a given word? Okay. The next probability table is what's called a state transition table, which is the probability that if we're at a current state or part of speech tag at the ith token in the sequence, what is the probability that we would observe or generate any given state or part of speech tag in this example in the next token in the sequence? And then we have some special probability tables that talk about, what is the probability of the first state from some special start state, sort of like beginning of sentence. And then some people use also a probability of transitioning from your last token or last state to a special end state. So this fully defines a hidden Markov model in terms of the parameters. And now we can put it all together and think about it in terms of a probabilistic modeling perspective. So again, we're going to go back to a probabilistic graphical model. And I just barely touched on this at the end of the previous lecture when I was doing a survey over probabilistic models. And so let's just revisit this slide. So you've seen this slide before. So again, if you recall, the arrows in these probabilistic models correspond to conditional dependence assumptions. So just from these arrows, I can tell you that the joint probability distribution of X comma Y can be factorized into this format, where the top arrows correspond to these products, and the downward arrows, the vertical arrows, correspond to these products. And again, I could have a special start transition probability from Y0 to Y1, and a special end transition probability. And if I make no further assumptions, so these are the only structural assumptions I make on this problem, then each of these individual probability functions are specified using a lookup table. I should also mention why the color codes are a little bit different. I guess I forgot to do that last lecture. The reason why the colors are a little bit different is an assumption about what is observed and what is not observed in the training data. So hidden Markov models, as we'll learn by the end of this lecture, can be trained in both supervised and unsupervised ways. And in particular, the most general application of hidden Markov models assumes that the training data is just the X, and we actually don't observe the Y, and we must learn the Y from data as a latent variable or unobserved variable. And so one way to denote that we don't expect to observe this variable in the training data is to have a different color coding. And this is just one choice, which is fairly common, which is if you expect to observe the data, the variable in the training data, you shade it. And if you don't expect to observe the variable, it's a latent variable, you keep it like unshaded. But sometimes we can also have a supervised domain hidden Markov models as well, in which case we observe the y variables as well. But in the most general form, people can train on hidden Markov models in an unsupervised way. And so the y variables are actually not observed in the training data, as is the case for mini project 3, following homework 6, where you have to model sequences of words coming from Shakespearean sonnets, where we don't observe the part of speech tags. At least you can annotate them, but just from the text itself, you don't observe them. Okay, so just to summarize, putting the previous 2 slides all in one slide. This lecture is about probabilistic modeling, and about probabilistic modeling over something more interesting than just naive Bayes, and we're going to go do hidden Markov models. And we start with the goal of modeling this joint distribution of x comma y, where x and y are both sequences of variable length. And again, just like in the naive Bayes lecture, if we don't make any assumptions, this model is just completely intractable, because we'd have to model using a lookup table for every unique combination of x, y pairs of variable length, which is just completely intractable. And so we make some structural assumptions, just like in naive Bayes. And our structural assumptions are such that we can actually flexibly model sequences of variable length. And again, just like in any graphical modeling or probabilistic modeling paradigm, we leave the main thing that we're trying to capture with this structure is conditional independence assumptions that allow us to model things as a product of smaller probabilities. In the absence of making any further assumptions, these individual smaller probabilities are typically modeled using a lookup table that enumerates overall the possibilities of the smaller table. Okay, so just like in the previous lecture, we can go through a few exercises like this one, where we can say, okay, we have the joint probability. What's the probability? We can use some inferences, like if we successfully learn the joint probability, we can compute the probability of x given y, where x is a sequence and y is a sequence. And in this particular case, because of the nature of the conditional probability tables that form the structural assumptions of the hidden Markov model, this actually completely factorizes into a product of independent probabilities. So conditioned on all the y's, all the x's are independent. That's an assumption of the hidden Markov model. Okay. So now we can ask, okay, we make these structural assumptions, and then we can say, okay, well, what are we actually modeling? So the second term here, this p of y I plus 1 given yi, is basically what's the complexity? It's the number of state-state pairs. So in our example, in part of speech tagging, the number of possible state-state pairs is 6 times 6, which is 36. So the size of this lookup table is 36. And then this probability table is called is often referred to as the state observation pairs, which is the number of different part of speech tags, 6 times the number of different words in your vocabulary. Some number, let's say 1,000, 10,000, 1 million, something like that. And then the bottom two are not even probability tables; they're just probability vectors, because it's always going to or coming from a single state. It's a single probability vector that sums to 1. So those are pretty cheap. Now you might ask the question, what's the relationship to naive Bayes? Well, there's a few different ways to think about this relationship, and they're all kind of equivalent. But I'm going to present it from the following perspective. In naive Bayes, we have a similar model where you first generate the y, and then condition on the y you generate the x. That was the sort of the big thing that we talked about in the previous lecture. And furthermore, you may have many different x's that you're generating simultaneously that are conditionally dependent given the y. But let's say we're only generating one x. And then we don't really model relationships between different x's. So this is what a naive Bayes model looks like. There's no dependencies between the different tokens in the sequence. In a Markov model, we have this conditional dependency between the y's in the sequence. But again, conditional on all the y's, the x's are all conditionally independent, just like in a naive Bayes model. And this is somehow the key to, that's somehow one of the key structural assumptions in these types of approaches that allows you to build these models that are very tractable. And you can do various different types of inferences in a tractable way. Okay, so just to go through an example. Suppose that we've learned a simple state observation probability table, which is P of x given y. And there are two part-of-speech tags and two different types of words. So vocabulary size 2, the number of part-of-speech tags is size 2, so this table is a 2 by 2 table, so size 4. If we want to model the probability of any sequence of x conditioned on some sequence of y's, again, according to our modeling assumptions, this completely factorizes into a product of independent probabilities that we look up in this table. So the probability of fish sleep, given probability of noun verb, is basically this 0.8 times fish sleep noun verb, this 0.5, and so on and so forth. So, did I make a mistake? Yeah, that's a typo. That's a typo. Let's go over there. Okay, moving on, I'll remember to fix that. Again, HMMs are generative models, which means that they model the full joint distribution of x comma y, which means that they can generate samples from a distribution. If you have a training set of data, you can apply this model to this data set, and because it's a generative model, of course you make some assumptions to keep the modeling tractable, but if you fit the model well, or the model is a good fit, then you've learned an approximation of the generating distribution that generated this data, which means we can generate samples from this distribution, and this is actually the thing that you're going to do in mini project 2. Excuse me, mini project 3. The first, we can consider the conditional distribution. So if we condition on a tag sequence, so we've already sampled the y's. We just want to sample the x's conditioned on the y's. Then we just basically for for each word in the output sequence of X, we just look up this table and flip a coin and then generate a sequence. And each X is generated independently according to the hidden Markov model and assumption. Okay, so that's pretty easy, just because of the structural assumptions of the hidden Markov model. If we're given a Y, sampling the X's is very simple. We just sample each individual X completely independently. What about sampling from the joint distribution? And so that's done using what's called a forward sampling process. It's also fairly simple. Again, keep in mind that there's a topological order to this graphical model, where you first sample y1, and then condition on y1, you can sample either x1 or y2. In fact, they don't condition on y1. Condition on y1, both x1 and y2 are independent of each other, so you can sample it in either order. And then after you sample y1, you can sample y2 given y1, and then after you've sampled y2, you can either sample x2 or y3. They're again condition independent. So as long as you obey the topological order specified in the hidden Markov model directed acyclic graph, you can just write a for loop over that topological order, or iterate through that topological order, and then just sample, because every time you do that local sampling, you're already conditioned everything else that's already been sampled. Yes, question?
So it would be fine to run the Markov chain and get all your Y's first, and then get all of the X's afterward.
For a hidden Markov model, yes. That might give you some pause about whether or not this is a good model, because that seems weird. But yes, that's right. So another way to think about just this P of Y. So to your point, we could talk about sampling the sequence of Y's first, and then after we sample the entire sequence of Y's, we sample the X's independently. And so one way to think about that is, well, let's just look at this sequence of Y's, right? We can model that using this transition diagram. So what is this transition diagram saying? We have some start state, and from the start state, in which I'm not depicting the probabilities here, we go to a noun with 80% probability, then we go to a verb with 20% probability, and then we're in the noun state. We go back to noun with 10% probability. We go to verb with 80% probability. We go to end with 10% probability. We're in the verb state. We go to verb with 10% probability. We go to noun with 20% probability. Go to the end state with 70% probability. And so we can, sampling the sequence of Y's is like doing a random walk on this graph according to the transition probabilities, and starting from start until we hit end. Yep. So this is the algorithm. And again, you can sample all the Y's first and store them somewhere, and then loop back over the Y's and sample the X's, or you can just do it in this interleaved way. We could also, one place where you can ignore this this term, although you could also use it if you want, is if you condition on length. So this is a little bit of, this depends on how you choose to model things. And so it's not entirely, it's not entirely consistent in the community. I just want to make that clear. But if you say I definitely want to sample a sequence of length, I guess there should be M, not L, just to keep the notation consistent, but of length 20, then we can do something like this. So sometimes you don't want to specify the length. You can do whatever length you want it to be. Sometimes you say, I do want to specify. Okay. Going back to summarize the model, what I've talked about right now, up until this point, is what's called a first-order hidden Markov model. And these are called memoryless models. So it turns out that if you try to write down the following conditional probability of the future x's and the future y's, given the first k x, given having already observed or sampled the first k x's and the first k y's, it turns out that the only thing that the future sequence depends on is yk. You can prove this by just looking at the independence assumptions of the hidden Markov model. And so people call these type of models memoryless models, which means I don't actually need to know what happened in the past. All I need to know is the current state of it. However I got to this current state is irrelevant in terms of forecasting or predicting or sampling the future states. And it is this memoryless property that is what is exploited to make hidden Markov models tractable. It also creates this weird, sometimes weird interpretation where if you want to do sampling from hidden Markov model, you could just sample the sequence of y's first, and then sample the x's afterwards, which sometimes seems a little bit weird depending on the application you're studying. Any questions? Okay. For the remainder of the lecture, I'm going to talk about two algorithms. Primarily talk about two algorithms. The first of which is the Viterbi, which I spent the most time on, because the other algorithms are going to be structurally very similar to the Viterbi algorithm. Raise of hands, how many of you have taken dynamic programming before? No one? Okay, I highly recommend going to recitation on Thursday. The most common prediction problem in a hidden Markov model, after you've trained it, so you fully trained the hidden Markov model, given an input sentence x, we predict a part of speech tag y, sequence y. So that looks like this. So this looks a lot like your standard supervised learning prediction task after you've learned your model. So, and this is indeed one of the most common prediction problems that people study in hidden Markov models. So the naive approach is to write a for loop over all possible y's and choose the one with highest probability. That's really bad, right? That's a for loop that will scale exponentially with the length of the sequence. We don't want to do that. So we're going to do some tricks, and we're going to use the Viterbi algorithm to do this more computationally efficiently than exponential time. And the Viterbi algorithm is the instance of what's called dynamic programming, which I believe it's covered in CS155, which is, I think, technically a prerequisite for this class. Okay. So first, recall Bayes' rule. We have P of, we want to predict P of y given x, and the only thing we care about is the max, in this case, the only thing that we care about is the maximizer. So the y that maximizes P of y given x. We exploit some properties of conditional probability, which is basically what Bayes' rule is built on top of. And then we, because we don't care about the x at the bottom, because it's fixed, and we're just trying to find the maximizer, and the denominator is always fixed for the entire computation of P of y given x. It just reduces to this problem. So finding the maximizer of P of y given x is actually equal to defining the maximizer of p of x given y times p of y for a fixed x. So x is fixed and y is the free variable in this maximization problem. And you'll recall that p of x given y is this product of independent probabilities, and then p of y is this product of the state transitions of the sequence of y. Okay, so the first thing we do is we write out this maximization problem, and then I'm going to do I'm going to just regroup the variables. This is a trick that's very often used in dynamic programming, where we regroup the variables. So nothing has changed from the first line to the second line. Absolutely nothing has changed. The only thing that I've done is I said, well, I'm gonna, because I'm just gonna treat the last variable, the very last y in the sequence, as its own little maximization problem, and then the other first n-1 y's I'll keep lumped together as a joint maximization problem. So this gives you the exact same solution, but I'm just gonna decouple the two these two sets of variables. And then you get something that looks like this, right? So before this product of probabilities is the exact same thing that we had before. And now I'm going to isolate out. I'm going to pull out all the terms that have y sub m in it. I'm sorry, y superscript m in it. And if you recall from the definition of the hidden Markov model, there are only two terms. I'm ignoring the transition to the end state here, just to keep it simple. There are only two terms that depend on y superscript m, and that is the transition from the previous state, so this probability table, and the observation. What is the probability of observing xm conditioned on having y on? Again, x superscript m is fixed in this particular problem. And the free variable that we're looking at right now is y superscript m. And then the rest just look like this, right? The rest of the probabilities fit into this probability function here. So what have I done? Yeah. So what have I done? I'm basically going to set up a recursive definition of this problem that leads to a tractable algorithm. In particular, I talked about the memberless property for quite a bit in the past few minutes. What's happening here is that we're actually going to exploit this memberless property to efficiently compute this maximization problem in a computationally tractable way without having this exponential blowup. And we're going to exploit the fact that the choice of y superscript m only depends on the first m-1 via this particular probability table. Otherwise, solving the optimization problem for the first m-1 y's is almost disjoint from solving the optimization problem for y superscript m. The only connection between solving the first optimization problem for the first m-1 y's, the only connection is through this particular probability table. Excuse me. Through this probability table, and otherwise it's completely independent, and that's what we're going to exploit. And that's what dynamic programming does. Dynamic programming works on these, well, there's two-dimensional dynamic programming problems as well, but this is a one-dimensional dynamic programming problem, and it works on the fact that you can actually solve these sub-problems of this bigger problem efficiently, and you can exploit this sub-problem to solve a bigger version of the problem more efficiently. And so what I'm going to describe is an instance of dynamic programming for one-dimensional problems. So sequences. For 2D, it would be a dynamic programming over a 2D array, but we're just going to look at the 1D case. So the key subroutine is, or the key subroutine is that we assume that we have computed the best length k prefix ending in each part of speech tag. So this is a little bit of a the notation is a little bit heavy, so, and I apologize for that, but once you get comfortable with the notation, the algorithm is very simple to understand. So the hardest part of this whole process is actually understanding the notation. So the setup. The setup is actually the hard part, and then the algorithm itself, once you understand the setup, is quite straightforward. And so let's walk through this notation very carefully. So capital Y hat, superscript K, of V, where V is verb, is the best length K prefix sequence. So a length K sequence of Y, or the Y variables, that ends in verb. So the kth part of speech tag is verb. So we can write that down formulaically as the following. So we're going to optimize for the first K minus 1. We're going to optimize for the first K minus 1 Ys that has the maximum probability, conditioned on observing the first K X's, and then appending verb to the end. So this loops over all possible Ys of length K that ends in verb and picks the one that maximizes this probability. That's the definition of that. Similarly, we can do the same thing for noun, right? So the best length K prefix sequence of Ys that end in noun can be defined similarly. We run a for loop over all sequences of the first K Ys that end in noun. And we pick the one that has the maximum probability for this condition of observing this X. Yes?
Is that a conditional probability or the joint?
So yeah, I was a little sloppy here. It turns out it doesn't matter because of this. It turns out it doesn't matter.
Oh, sure.
Because of this, because we're solving the argmax problem of Y condition on X being fixed, and so the denominator here is always fixed for everything we're observing. Mm-hmm. It turns out that for purposes of finding the maximum Y, it's all rank consistent, so it doesn't matter.
Okay.
But if you're not solving the maximization problem, of course it matters. And I'm getting ahead of myself, which one you use is whichever one is easier to implement, because they're mathematically equivalent. Okay, so the claim, and this is the key claim that underpins all dynamic programming approaches, is the following: that if we assume that we've already solved these subproblems up to length K, and now we want to solve the subproblem up to length K plus 1, what do? Do we just run a for loop over all length K plus 1 sequences, or can we somehow use the first the solutions, prefix solutions we computed previously in a way that makes the whole algorithm computationally efficient? That is the key to all dynamic programming approaches. And so here's the claim: if we want to compute the best length K plus 1 prefix, and now length 1 greater, if we want to compute the best length K plus 1 prefix, that in this case, let's say ends in verb, we don't need to run a for loop over all length K plus 1 prefix sequences of Y. We only need to run a for loop over the solutions of length K that we previously computed. So we previously computed all length K prefixes that end in some part of speech tag. I'll denote that by a free variable, capital T. And in the running example in this lecture, there's 6 of them. So in order to compute this guy, we only need to do this. So this is a for loop over 6 things, as opposed to a for loop over 6 to the K plus 1 things. Okay, and furthermore, you may want to actually, so even though the for loop, the argmax, the for loop here is short, you may want to also compute this value efficiently. So you don't want to waste too much computation recomputing this value. And of course, we can factorize this using the hidden Markov model with factorization assumptions. And again, some of these, as long as you store some extra things, these were pre-computed. And as you may have suspected, this is a recursive definition. And typically the way you prove correctness of dynamic programming is using inductive proofs. So you have an inductive hypothesis, you have a base case, you have an inductive case. You prove that this recursive definition is always true, and then at the end of the whole procedure, some property holds that you can show that this whole thing is correct. And I'll get to that towards in a few slides. But first, this is sort of the central claim of how the algorithm works. Okay, so I'm going to go through a very small example. Excuse me. So in the base case, we are at the first token in the sequence, in which case the best length 1 sequence that ends in verb is just verb. The best length 1 sequence that ends in determiner is just determiner. So the base case is trivial. And we store both the best length 1 sequence that ends in a particular part of speech tag, as well as its probability. And we store this just for bookkeeping to make computing the future probabilities faster. And in this example, there are only 3 part of speech tags, otherwise the slide gets too messy. Okay. And now, here's the inductive case. We want to compute the best length 2 sequence that ends in verb, determiner, and noun, respectively. And so the algorithm basically does the following. And we're going to first look at the best length 2 sequence that ends in verb. And it runs a for loop over the best length 1 sequence, all the best length 1 sequences, and it considers appending verb to the 3 best length 1 sequences, computes this whole probability, and then picks the one that's best. And let's say it's noun. That one has the highest one. So this is the best length 1 sequence that if I append verb to it, so noun verb, it gets the highest probability. And we do that for the other 3, so the other 2 as well. So for the best length 2 sequence that ends in determiner, we run a for loop over all 3 length 1 sequences, and we consider appending determiner to all of those 3 sequences, and we pick the one that has the highest probability. And again, for the best length 2 sequence that ends in noun, we run a for loop over the best length 1 sequences, consider appending noun to those 3, and choose the one that has the highest probability. And then we store the length 2 sequences and their probabilities, just for better bookkeeping. And we do it again. So now we're going to compute the best length 3 sequence that ends in verb, determiner, and noun, respectively. And again, for the best length 3 sequence, prefix sequence that ends in verb, we run a for loop over the best length 2 sequences. There are 3 of them in this example. We consider appending verb. To those length 2 sequences, and we take the one that has the highest probability. And so another way to restate the claim from the perspective of this pictorial example is that when we compute the best length 3 sequence that ends in verb, we don't need to go through all possible paths, through this graph. We only need to go through the paths that are still alive that get to this stage. Okay, I'll give you a sketch of the proof. It's not the full proof, but it gives you a flavor of what the proof looks like. Suppose for the sake of argument, so this is a proof by contradiction. Suppose for the sake of argument that this was the solution that this algorithm returned. So this algorithm, the Viterbi algorithm, returned this as the best length 3 sequence that ends in verb. Again, x is always fixed for any instance of this problem. So we're conditioning on x. And then suppose that something else has higher probability. So the problem is that what if something else had a higher probability, but it was eliminated. But see, there's no way. Okay, let me backtrack slightly. So suppose that suppose we try to prove that something else had a higher probability, even though the first one, verb, 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 was the output of this algorithm for a length 3 sequence that ends in verb. Suppose that somehow noun, verb, verb has a higher probability as a length 3 sequence than verb, 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 and so our algorithm is wrong. It did not find the best length 3 sequence that ends in verb. Well, we can actually look at, we can actually look at the terms, right? So all the verb, 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 and noun, verb, verb differ in 3 terms. They differ in this guy, and this guy. Because the difference is in the first token, right? So these are the only 3 things that depend on the first token. None of these 3 things depend on Y3. None of these things depend on Y3. So by the inductive hypothesis, if verb verb was the best length 2 sequence that ended in verb, but then noun verb could not have been the best length 2 sequence that ended in verb. And appending verb to the end of it doesn't change that fact, because Y3 doesn't influence any of these terms, which was used to select the best length 2 sequence that ended in verb. So that's the core idea of how you prove that this algorithm is correct. The full proof, of course, is more general. This is grounded in a specific example. And this is directly exploiting the memoryless property of hidden Markov models. Okay. So, that's the Viterbi algorithm in a nutshell. Okay, so here's how you use the Viterbi algorithm. Here's how you use the Viterbi algorithm to actually solve your original problem. So, look, we want to solve this problem. We can make it equivalent to solving this problem. And then we run the Viterbi algorithm that loops through from length 1 sequences to length capital M sequences, where capital M is the length of the x. And we iteratively solve for these best prefix solutions using the Viterbi algorithm. And then after we've run the Viterbi algorithm, we look at the best length M sequences. There are 6 of them in the general example. In the general run example in this lecture, there are 6 of them. And we just run a for loop over those 6 and pick the one that has the highest probability, and we're done. Because the best length 6 sequence is the best sequence for the entire problem. Sorry, the best length M sequence is the best sequence for the entire problem. Okay, we're going to do a short numerical example. So this one's even simpler than the previous one, just so it all fits on one page. Sorry, excuse me. Let's see. The input x is fish sleep, so that's the fixed x we're going to fix. We're going to compute the best length to y. So we start. So how you read this is you start from the start state, and then you look at this probability transition table. Probability transitions encoded in this graph, which is equivalent to the probability state transition probabilities. And then you compute the best length one subsequence that ends in verb or noun. So that's basically a product of transitioning from start to verb times the probability of observing fish condition on verb, and the transition from the probability of transitioning from start to noun times the probability of observing fish condition on noun. And we pick the one that's higher, which is the bottom one, 0.64. Sorry, I jumped ahead of myself. We commit to both of them. We commit to both of them because these are respectively the best length one subsequences that end in verb and noun. We keep track of both of them. And then we go on to the second token, which is sleep. And we consider transitioning from the best length one sequence that ends in verb to verb and noun to verb. We multiply the probabilities together, that's what you see down here. And that's the respective probabilities of transitioning from this guy here, and this guy here, and this guy here, and this guy here. We pick the one that's higher. And then we find the maximizer, which is you can even read off the sequence by just looking at this arrow backwards. So the sequence that has the maximum probability is fish sleep. Okay. Can anyone tell me what might go wrong for long sequences? For this, if you look at this numerical example.
Underflow?
Excuse me?
Underflow?
Correct, underflow. So the numbers, because everything's less than 1, these numbers can get exponentially small as the sequences get large in length, which is the problem. And so in general, people implement the Viterbi algorithm using log probabilities rather than probabilities. And so rather than solving this argmax, because log is a strict monotonic function, it preserves the maximizer. And so you can take the log, and then you do the log. And so instead of this product, you do the log of this table plus the log of this table, and you get the exact same solution. But now you're storing log probabilities, and you're adding them together as opposed to multiplying the original probabilities. But nothing else changes. This is how you correct, but this is how you correct for underflow. Okay, so just to recap, we want, because modeling all the sequences jointly is too complicated and modeling all things independently is too simple, we want to actually be able to model context between multiple words. And that's why we looked at hidden Markov models. But the problem with hidden Markov, or one of the challenges with hidden Markov models, is that in order to predict something like the maximum y given x, p of y given x, or the y that maximizes p of y given x, you have to actually be able to solve this problem efficiently. And a naive algorithm that runs a for loop of all possible sequences of y scales exponentially with the length of the sequence. And that is why people use the Viterbi algorithm, the same Viterbi that is named after the School of Engineering at USC, by the way. to actually compute this maximizer efficiently. I should emphasize that, again, if this is the first time you've seen dynamic programming, it's okay. We will have a recitation on dynamic programming. I believe it's this Thursday. And dynamic programming is a general concept that is very powerful and is arguably one of the most powerful things that has come out of computer science research because it studies the structure of computation. If you can structure your model in a certain way, you can exploit the structure of those data structures to arrive at algorithms that are way more efficient than a naive for loop over all possibilities. And the particular structure that we're exploiting here is the memberless property of hidden Markov models. Okay, so I'm going to spend the rest of the lecture talking about training. And the reason, and one thing that will become apparent is that during training you also have to run a dynamic programming algorithm. But I'm going to go through that a little bit faster because it has sort of the same structure as the Viterbi. But we're going to start with supervised training. Supervised training is kind of weird, or not weird, but well, yeah, it's a little weird for hidden Markov models because hidden Markov models were designed initially for cases where you don't observe the y's. But suppose we do observe the y's. So our training set is a set of xy pairs of sequences where the x, as in our running example, is a word sequence, and the y's is a part of speech tag sequence. And the goal is to estimate p of x comma y from this training set. So we're going to do this using maximum likelihood, like all probabilistic modeling approaches. We can have this, I talked about this briefly before, we can have these transition matrices where you can have, where people often write these things as matrix form just to make the notation simpler. It's sometimes to leverage matrix multiply, parallelized matrix multiply operations that are available on CPUs and GPUs. And so there's nothing special here, I'm just noting that there's a matrix to form where A is the transition matrix and O is the observation matrix. And those correspond exactly to the probability tables. So there's nothing special going on here, just a change in notation. Okay, maximum likelihood. If the data set is fully supervised, it turns out that you can solve everything by just counting. So what does that mean? That means the transition probability of going from B to A is equal to the numerator is the number of times in the training set you've observed the Y going from B to A, and the denominator is the number of times you observe B in any given one. So this is just a conditional probability that you've observed a Y in one of your sequences in your training set, and the probability, observe the B, observe the B, and then the next Y is an A. That is just an empirical frequency count of that conditional probability. Similarly, for the observation matrix or the observation probability table, it's again just an empirical frequency count. So if we have a part of speech tag, generic part of speech tag Z, and a generic word W, then the numerator is the number of times in any sequence, in any training sequence in the training set, the Y was a Z, and the corresponding word X in that token was a W, and then divided the total number of times we saw that part of speech tag in the training set. This is an empirical conditional probability frequency count. And you could derive this as the optimal solution if you minimize the negative log likelihood of the top guy and you find where the gradient is 0. We saw that example in its full derivation for naive Bayes in the previous lecture. The way you derive this is basically identical. It's just slightly more complicated. Okay. Superheated, right? And okay, but we also care about the unsupervised case. But to maybe dig a little bit deeper, one of the reasons, and this is just the one extra thing on top of naive Bayes, is that because of the conditional independence assumptions of the hidden Markov model, where the only thing, if you condition on this y, everything else is independent, everything decomposes into this product of pairs. And so that's the one extra thing that's on top of the hidden Markov, on top of the naive Bayes assumption that you need to sort of work through in order to get to derivation. Get to the derivation, and once you sort of work through that, then then you can just take this exact derivation that we saw in lecture in the previous lecture, and then just apply it. So one question is, what are the number of parameters? And this is, of course, very important as well. And the number of parameters is the transition matrix is the number of tags squared, and the observation matrix is the number of words times the number of tags. So one of the key benefits of this approach is that it avoids directly modeling word-to-word pairings. It avoids the probability of observing the next word conditional on observing the current word. Because typically the number of tags is much smaller than the number of words, and these are, of course, a very conservative estimate of the number of words, 10,000 or so. And so the first, if it were 10 and 10,000, then the A matrix has size 100, and the O matrix has size 100,000. Whereas if you directly model word-word transitions, the O matrix will be huge. But of course, by the price we pay by shrinking the model using a hidden Markov model assumption is that some sequences are harder to model. Like, for example, we want to generate a sequence or sample a sequence. The sampling of the y's don't actually depend on the x's at all. And that could be a reasonable assumption in many applications, and it could be kind of a weird assumption and bad assumption in other applications. Okay. Now let's talk about unsupervised training. So no y's, just a sequence of x's. So for example, in mini project 3, you have a sequence of Shakespearean sonnets, or a sequence of each x is a Shakespearean sonnet or a sentence in a Shakespearean sonnet. And we still want to estimate p of x given y. Perhaps the first question is why would we want to do that? Why don't we just directly model p of x? So, maybe just to touch back on why you do unsupervised training in the first place. So supervised data is hard to acquire. As we saw in the first half of this course, it's actually quite challenging in many domains to have a target label that you want to predict. But unsupervised data is plentiful. You can just grab all the text on Wikipedia, New York Times, Reddit, whatever, Twitter. Maybe not Twitter, but and we can learn the y's as a latent variable. So we're going to learn a set of y's that maximize the probability to be able to reproduce the data that we see. And like all generative models, you may not know what you want to use this model for, but you can use it, if you estimate the model well, you can use it for other downstream tasks. Okay, So if we already had the y's, then maximum likelihood is trivial. We just do frequency counts. If we had the parameters of our model, the A and O matrix in particular, and then of course the special starting and stop transitions, I'm just sort of ignoring those for now, then we can predict the y's. Okay, seems like a chicken and egg problem. If we had one, we get the other, we get the other, we get the first one. Okay, so here is the algorithm. It's called EM. E stands for expectation, M stands for maximization. It's a classic algorithm. It goes under many other names. EM is the generic name for this class of algorithms. The specific instantiation of EM for hidden Markov models is called a Baum-Welch algorithm, named after its inventors, but it's just a special case of a general class of EM algorithms, which we cover. We covered another EM algorithm for k-means, if you recall, from like 4 weeks ago or something. So here's what we do. We initialize the parameters of our model arbitrarily, let's say randomly. We predict the probability of the y's for each x in our training set. And then we use those predicted y's to estimate a new model. And then we loop until we converged or met some convergence criteria. That's the EM algorithm. So the expectation step is the hard part. So we want to, given a fixed parameterization of our model, we want to predict the y's given an input sequence of x's. And in particular, we want to predict P of yi. So what does this mean? This means that we want to predict the marginal distribution of each yi. So what is the probability, given that this is the sequence, what is the probability that at this token, averaging out all the other tokens in the sequence, at y's in the sequence, what is the probability, marginal probability that for this token in the sequence, I observe yi as noun or verb or determinant? And that's what you see in this table. This is what we want to estimate. I'm a little short on time, so I'll skip this slide. The maximization step is straightforward. So, we have this is the supervised version of the problem where the yi's are annotated exactly. In the EM version of this problem, we have these probability distributions over what the y's might be. That's what we compute using that's what we use in the previous version of the hidden Markov model. So we just do this soft counting rather than hard counting. But otherwise, it's basically the same. Yes, question?
Why do we even need the probabilities of the y's? Why not just use Viterbi to find the most likely y's and then just do the maximization step?
You could. Okay. It's a bit brittle because you want to be robust here. You want to be able to talk about uncertainty, like, oh, I think it's 50-50. But I think it's 50-50 between two different options. That's encoded in this type of soft counting. So it's a lot less stable to do Viterbi. But the algorithm for computing these is very similar to Viterbi.
Okay, but then you just have to run it for each separate y. So it'd be the time complexity would be
the same as Viterbi.
Oh, the same. But then you have to run it for each state y. Or
yeah. I'm running a little short on time. I only have about 6 minutes left. But that's going to be the last thing I'm going to talk about. So, but just to reemphasize, if we could compute these probabilities of these assignments, then we could just do the soft counting. It turns out that the solution to these optimization problems, to these maximum likelihood problems, is the same form. It's just that here we're doing hard counting because we have a direct annotation in the supervised case. Here we're doing the soft counting. That's it. Okay. So the last piece is how do you actually compute these probabilities? And that's done using what's called the forward backwards algorithm, which is very, very similar to the Viterbi algorithm. It's just computing a different thing. So the notation is very similar. So we want to, instead of computing the best possible single y, we're going to compute this probability, which is given the first. This is a very common notation. In fact, I think I took this notation from Wikipedia. We have these alpha beta vectors. The alphas are called the forward vectors, and the betas are called the backwards vectors. So alpha says, I'm going to compute the marginal distribution, given some current parameterizations of a hidden Markov model, of the probability that the ith token, the ith y, is some part-of-speech tag z, determiner, noun, verb, could be anything, given observing the first I x's. And the backwards vector, the beta vector, says, I'm going to compute this probability, the probability of observing x1 through capital M, so the future, conditioned on yi equals z and the parameters of our model. It turns out, and this is a very simple thing to check, that if you have these alpha and beta vectors computed, if you can compute these alpha and beta vectors, then this probability is just a very simple formula of these alpha and beta vectors. So this is very efficient to solve. This is very efficient to compute. It's just a for loop over 6 possibilities, the number of z's, the number of part-of-speech tags. So the game that we play is how to compute these alpha and beta vectors efficiently, because nominally you have to marginalize out over all the other y's in order to compute this just for yi. And just to quickly state, if you want to compute a transition from A to B, it's a little bit more complicated, but again, it's just a double for loop over 2 different pairs of part-of-speech tags. So the denominator is 36 instead of 6, but still it's quite computationally efficient. And again, you can work this out for yourself offline. It just falls out of the formula for a hidden Markov model. So the game is to be able to efficiently compute these alpha and beta vectors without having to loop through all possible sequences of y's to average out over the y's that don't matter in this. So the forward sub algorithm, again, naively, in order to compute this quantity, we'd have to sum over all the other y's, right? At least the prefix y's, which is exponential in this naive for loop case. And the trick is that we can compute this alpha quantity recursively, just like in Viterbi. But whereas in Viterbi, we took a max. We only took a max over one of these to compute this probability, and we kept track of that max. In the forward algorithm, we take a sum, a weighted sum. I know I'm going over this a little bit fast. I'm going to go over this again on Thursday. But structurally, it's sort of that's the connection. Right. So Viterbi effectively replaces the sum with a max operator. The backwards algorithm, again, running this for loop over all the subsequence of y's is exponential in the length of the subsequence. And again, we have it's a little bit weird to when you first see this, but it's structurally the same. You just have to do it backwards over the sequence. And again, you have the same, the same weighted sum over this recursive definition going backwards in the sequence instead of going forwards. And so that's the forward-backward algorithm. We compute the alpha vector forward. We compute the beta vectors backwards. And then after we computed these vectors, we could compute anything like of this form by just this simple tractable formula of the alpha and beta vectors. Okay, so just to recap. Okay, I'm almost done. Sorry, I might go a couple minutes over, I apologize. So just to recap, in unsupervised learning, we have our training sequences are only the x's and not the y's. The y's are also known as hidden states. This is actually why this model is called a hidden Markov model. And we train using the EM algorithm, we converge to a local optimum. And the final thing is, well, how do we initialize? For example, how do we choose the number of hidden states? We don't know what the y's are. There could be y could be 6 categories, like the running example in this lecture. Y could be 10, y could be 15, y could be 20, y could be 1 or 2. And typically, the thing you do is you use validation data. So you do cross-validation. So just to recap, we have, today we covered a probabilistic modeling perspective on sequence prediction, which led to the development of the hidden Markov model. And the reason why we do this is that this model is compact. It only models pairwise comparisons, pairwise transitions between the y's. And because of that assumption, which is a very strong assumption, you can model sequences using very few parameters. The main limitation, just like in naive Bayes, is that it makes a lot of independence assumptions. We can, of course, lead to poor predictive accuracy, and that's why for supervised learning tasks, people usually use something like a recurrent neural network. But again, this probabilistic interpretation is very important, and it has many downstream applications. And we sort of and the hidden Markov model embodies the sort of simplest model that allows us to reason about these probabilistic interpretations. So the next lecture, so Thursday, because this topic is by far the most complicated topic in the lecture, in the class, I'm just going to go over the same topic on Thursday. It'll be an unstructured lecture, so please come with your own questions. And then next week, we'll cover some special topics in deep generative models that combines deep learning with probabilistic models. None of that's on any homework assignments, just for your enjoyment, and this recitation on Thursday on